Hey guys, so we're going to look at an example here of how we find and use the best fitting regression equation for a set of data. So you will use this idea you'll be getting your best fitting regression equation for your data analysis project on Google Sheets. We're also going to show you how to find a best fitting regression equation in your calculator. So it's very similar. It's the same idea, but there's a different process that we have to go through in the calculator for finding that regression equation. So the first thing here, let's look at the example. The height and weight of several adults were recorded. So I've got my height and weight table of data here. Part A is asking me to find the best fitting regression equation that models the height as X and the weight Y of adults. So since I'm working with a regression equation in my calculator, I'm going to come to mode and I need to make sure that my stat diagnostics are on. So you see here, I don't see stat diagnostics anywhere, but if I come down to where it says next, I'm going to go down. Again, now here we see right towards the center, stat diagnostics. Whenever you reset your calculator, the stat diagnostics get turned off, and we want them to be on. So I'm going to arrow to the right and press enter. Then if I do second mode, that quits out. My stat diagnostics are now on. The second thing I need to do before we can start looking at regression equations is go into my stat and edit. I need to enter this data into my lists. So I'm going to go to stat, edit. We'll put the height into L1 and the weight into L2. We want to make sure we're being very, very careful here to be completely correct, essentially, as we are entering the data points in exactly as we see them in the table. Once I get to my second list, my L2, I also need to make sure that my data points are lined up. So if I come over, next to 4.55, I must make sure I'm putting the 91.7. So we need to make sure these are lined up correctly. Otherwise, the calculator is going to do different calculations than what we want. So I'm just being very careful here as I enter in this data to make sure. So you'll notice a good check is that I have every single data point all the way to the last one, 6.45 feet and 187 pounds. Those line up correctly. Now that we've entered the data, we are ready to start using our regression equations. So we're going to come back into stat now, and we're going to come over to calculate. And we're going to use something new in here. I'm going to type these out. We're going to use linreg for linear. So for our linear regression, we're going to use linreg. For our quadratic regression, we're going to use quadreg. And for our exponential regression, we're going to use expreg. And so really what we want to start with is just finding the r squared value for each of these. We're specifically going to be looking at r squared because all of these have an r squared. They don't all have the r, the correlation coefficient. So if I come down here to number 4, that'll be my linear regression, linreg. Press enter. Make sure my X list is L1, that's where we put the height. My Y list is L2, that's where we put the weight. Make sure my frequency list is empty. We don't want anything in the frequency list. And we'll come down and calculate. So as we walk through here, the top, this will be the same for every single one of these regressions. This very first line here is going to give me the format of the equation. So for the linear regression, it's y equals ax plus b. And then it tells me what does the a equal for this set of data? What does the b equal for this set of data? And then in this case, I have both the r squared and the r. Now again, we are looking at r squared. So I'm just going to type that in here. If I was writing this, I would write it out. So my r squared equals 0.995. I'm just going to write that down so that I can come back to it later, because again, I want the best fitting, and the best fitting r squared, to remind us, will be the one that's closest to 1. So that's pretty darn close to 1. It's almost exactly 1, but let's see what the quadratic and the exponential give us as well. So I'll come back to stat, over to calc, do my quad reg next for my quadratic regression. X list L1, Y list L2, frequency list empty. So we'll come down and calculate. And for this one, ooh, see, it's just ever so slightly better. My r squared for this one, r squared is equal to, and I want to be careful with my rounding here, 0.9968 would be 0.997. So it's just an ever so slightly better fit than the linear, because it's just a little bit closer to exactly 1. And then finally, we'll come over to our exponential. So stat calc. You'll notice you don't see the exponential here. So it's actually on the next screen. So if we come down, number 8 is another linear regression. Number 9 is the ln, that's a logarithmic. 0 is our exponential regression. So x list L1, y list L2, nothing in frequency list, so I can calculate. And my exponential regression gives me an r squared of 0.993. So as I'm looking at these, I'm again, which one is the best fitting? These are all good fits, but we're looking for the best fitting regression equation. So in this case, the best fit, because the r squared is closest to 1, the best fit is going to be my quadratic. Now I'm not going to stop here. I have to go back and figure out what was that regression equation. So we'll go back to our quadratic regression, which was number 5. And we're going to write out our equation. So coming down to calculate again. Oops. Notice that the format here for this equation is y equals ax squared plus bx plus c. That should be familiar. That is our standard form of a quadratic. I'm going to insert an equation here just so it types a little bit nicer. So I'm going to start with y equals, and instead of typing the a, b, c, I'm going to use the values here below as my a, b, and c. We don't have to type out all of those decimals. That's a lot of decimals. But let's go to the hundredths. Let's go to 2 decimal places. So we'll do 3.774, because the 8 comes after that 3, x squared. Plus, since the 8 is positive, plus 8.41x. And notice that the c is negative, so we can put minus 22.99, and that is my regression equation. This is the equation I'm going to use as we go through and we start using this equation to estimate or predict values. So let's go into part B. Using your model, this is my model, right? Using my model or my equation, what is the estimated weight of someone who is 5.7 feet tall? Well, all this is asking me to do is take 5.7, substitute it in for x. Oh, we forgot that part. X squared, don't know where that went. 3.74x squared. So we were going to substitute 5.7 into this equation and see what we get for y. So if we're typing that out, we'll have y equals 3.74 times 5.7 squared plus 8.41 times 5.7 minus 22.99. And let's see what that equals in our calculator. So we just press enter one more, second mode, that quits us out. We don't have to worry about that anymore. And let's just type this in. So 3.74 times x, no, I know what my x is. It's 5.7 times 5.7 squared plus 8.41 times 5.7 minus 22.99. Enter. So the estimated weight of someone who is 5.7 feet tall, and this asks me to round to the nearest tenth, is 146.5 pounds. All right, part C asks me, how does my estimated value of 146.5 compare to the actual data point in the table? Well, if I look at the actual data point was 148 pounds. So the estimated value of 146.5 is less than or smaller than the actual data point of 148 pounds for a person who is 5.7 feet tall. We can also actually find what that exact value is. Should put in my units there. So if we did 148 minus 146.5, we could add in by 1.5 pounds. So the estimated value of 146.5 pounds is less than the actual data point of 148 pounds for a person who is 5.7 feet tall by 1.5 pounds. Finally, according to the model, or according to the equation again, what would be the weight of someone who is 7 feet tall? Round your answer to the nearest tenth. Now, this is a prediction instead of an estimate. The reason is because we actually don't have a data point at 7 feet. We had an actual data point at 5.7 feet, but we don't have an actual data point at 7 feet. So now we're predicting what it would be. So we're going to do the same thing. We're going to substitute into the same equation. So y equals 3.74 times now 7 feet squared plus 8.41 times 7 feet minus 22.99. Use my calculator. To get an estimated weight of 219 pounds, 219.1 pounds. Now, this is also asking us, is this prediction reliable? Why or why not? So if we look back up when we're thinking about, is this a reliable prediction, we're going to be looking in this class at the R-squared value. Once we get into AP statistics and other statistics courses, you'll look at other reasons why a prediction may or may not be reliable. We're really going to focus on how well does the equation fit the data. So when we look at 0.997, that is a very, very strong correlation, which means that this is a very reliable prediction. It doesn't mean that someone who is 7 feet tall is automatically going to be exactly this weight, but we can use this as a very strong prediction because that's such a strong correlation. So we could say something like, prediction that a person who is 7 feet tall weighs 219 pounds, 219.1, pounds, is a reliable prediction because the correlation R squared is very strong. That's all we need for that. That tells us why. Because that correlation is very strong, we can reliably predict. We can use this as a reliable prediction. As you're thinking about each of the parts of this problem, this is exactly what you're going to be doing in part 4 of your data analysis project, except that instead of using the calculator, you'll be using your Google Sheets.